Hello and welcome to our first of so this is alternative delivery for March 17th of 2020 for the course 2115. Now looking back, there are some problems that will be useful for us to remember and in skills that will be useful for us to remember. So given these two relations R and S on a set A, which is 1, 2, 3, I'm going to ask you to find all of these things. All of these things were defined. Now what you really should do is pause this, work to get an answer, reviewing your notes perhaps, and then come back and continue, and we'll compare your notes with the solutions. So you should be pausing now and doing some work. So here are the answers that you should have gotten. R union S is this collection of ordered pairs. R intersect S is this collection of ordered pairs. This is a different notation, but that's the complement of R. And notice that we use the fact that A cross A is the universal relation on A, so we're using that as the set to which we draw the complement from. And whenever we compute R composed with S, the set we get are these set of ordered pairs, and if we just take S composed with S, these are the sets we get. So those are the answers that you should have gotten, and I encourage you to work through those and make sure that you understand those solutions. And here's another theorem for you to prove, and basically what we're proving here is that the composition of relations is associative. Now, one thing that we've said before, and we should know, and you should know, and you should be able to come up with a counterexample, is that the composition of relations is not going to be commutative, just like the composition of functions that you've studied in your other math classes are not commutative. But anyway, we're to prove that these are associative. So again, you should pause and try to prove this, and we'll go from there. Okay, so what you need to do is show that each ordered pair in this set also belongs to this set, and you do have to do it vice versa. Whatever starts in this set is in here because these are actually sets. So suppose AD belongs to this set, then there's a C in capital C such that AC is in RS and CD is in T. So since AC is in RS, there exists a B in set B such that AB is an element of R and BC is an element of S. So since BC is in S and CD is in T, we have BD is in S composed with T. And since AB is in R and BD is in S composed with T, we have AD is also an element of R composed with S composed with T this way. So what we've shown is that this set is a subset of that set. Similarly, we have to show that the subset inclusion counts the other way, but both of those together will prove our assertion. I think we talked a little bit about this last time, but it is a good review. A matrix is a convenient way to represent a relation from X to Y, a relation R from X to Y. And this is especially useful if you're putting this into a computer. So we label the rows with the elements in X in some order, and it does make a difference the order. And we label the columns with the elements of Y, again in some order. Then we set the entry in row X and column Y to 1 if X is related to Y, and to 0 otherwise. This matrix is called the matrix of the relation R relative to the orderings of X and Y that we have. Now, I did mention last time, and I reference it again, I know Dave came up with a QSR code or something like that, but if you go to this site, you can review matrices for those of you who are not taking linear algebra at present. All right, so here is an opportunity for us to do a couple of problems. And so we're given relations R, and what we're trying to do, and orderings of a set X and a set Y, and we're supposed to come up with the matrix of the relation And I guess we're doing this for different orderings, and we're going to get two different answers. So you should pause, do the problem, and then come back. Here are the solutions that you should have gotten. Now, those that are taking linear algebra might say that, oh, these are what we will call similar matrices because they can be obtained from each other by switching rows and columns, which are also known as elementary row operations. You don't have to know that, but that could help you. Here is an example where you have a relation defined on a set X. So that means that this set is set X and that set is set X, and it's in the same order. And notice that whenever we're going X to X, we always have a square matrix. This example is referred to in several other problems and illustrations. That's why I showed this one to you. Okay, so here is a problem statement then. You should read it, but basically what we're doing is we're starting with sets A, B, and C, and we have R and S relations, so we're finding the composition, and then we're supposed to find the matrices that are associated with R, S, and R composition S, and compare that R composition S to the matrix product MR times NS. Again, pause and see what happens when you work through this. Well, here are some solutions for the first part. What we're really trying to do is we end up with an R composed with S is the set shown there, and one way to get at it is to compute a little drawing like this and do the calculations associated with the drawing. When we construct the matrices, what we get is MR should be represented this way, MS should be represented this way, and the composition should be represented this way. If we multiply the two matrices together, this one times this one, and again the do-it-yourself review shows you how to do that, you get a matrix that looks like, well, the one that you get when you multiply them is down here. Now you notice that it's the same as this, except the 2 pops up, but that means any place where there's a non-zero element, that does represent it. So observe that these have the same 0 entries, and so that means that the places where they're not 0 follows, and you can in fact understand that that is a way to get at the matrix for the composition. We'll have a theorem later on that. We can quickly determine whether a relation R on a set X is reflexive because you just look at the diagonal. For example, this one is reflexive because A is related to A, B is related to B, C is related to C, and D is related to D. It is the main diagonal. So a relation R is reflexive if and only if you have ones down the main diagonal. You can also quickly determine whether a relation on a set X is symmetric by examining the matrix relative to some ordering, and it's symmetric if and only if, for all I and j, the ijth entry is equal to the jth ith entry, and that is what we call a symmetric matrix in your linear algebra class. So for example here, since you have a bunch of zeros, but here you have the CD element, and here you have the the CB element, and here you have the BC element. Those are both ones, so that tells us that this in fact is a symmetric relationship. And so we can also determine whether something is antisymmetric by examining the matrix of R relative to some ordering. This is a problem, and I would like for you all to ponder this problem, think about it, develop an answer. It is useful thinking about these things to develop your answer, and then we will look at a solution. And this is kind of an elegant way to write the answer, but for I different than j, aij times agi is equal to 0. One of them must be 0. Here's the theorem that we talked about, and this basically says if R1 is a relationship from X to Y, R2 is a relationship from Y to Z, and you choose some fixed ordering, and this is the matrix for R1 and R2 relative to those orderings, then R2 composition R1 is found by finding the product and replacing each non-zero term in the product by 1. And the proof of that follows very much the example that you went through. And there's another example in your text that has gone through. So there's a quick test for determining whether a relationship is transitive. If A is the matrix of R relative to some ordering, you compute A squared. We then compare A and A squared. The relationship is transitive if and only if, whenever the entry ij in A squared is non-zero, the entry ij in A is also non-zero. It's a quick proof using matrices. Here's a problem, and we talked about definitions of reflexive, symmetric, transitive, antisymmetric. We didn't talk today about partial order, but we did before. And is this an equivalence relationship? And we're trying to look at problem 10. So my question for you is problem 10 an equivalence relationship, or do those other things hold? So pause, think through it, and check your answer. We find that it is symmetric and transitive only. Another question, given a matrix that is R from X to Y, how can we find the matrix of the inverse relationship R inverse? Again, pause, think about the problem, come up with your answer, and check to see if it is a good answer. You take the transpose of the given matrix. Now, some of you may know what transposes are very well. Some of you may have to review that. It's important for you to realize it is not necessarily the inverse of the matrix. It is the transpose of the given matrix. And here we define what a transpose is, and a transpose is defined. So if you have a matrix that is m rows and n columns, the transpose is what you do is the rows and columns are interchanged. So here is an example. This is a 4-row, 2-column matrix, and the transpose is going to look like that. The transpose of a square matrix, of course, would be a square matrix. And if a matrix equals its transpose, it's called a symmetric matrix. You know this from your linear algebra, perhaps. And there's other problems that you can do here. I don't think I do any of those. But problems 19 and 20 I thought were worthy looking at. Given a matrix of a relation R on X, and this is an equivalence relation, how can you easily find the equivalence class containing the element X, an element of the set X? And the other question is talking about if you have R1 and R2, you can show that the ith kth entry of the matrix product A1 and A2 is equal to the number of elements in this set. So you should pause and think about this first problem anyway, problem 19. And what you conclude is the vector product of the row vector associated with the element X and the column vector that contains all ones, because the non-zero elements in the vector product will correspond to the members of the equivalence class of. I called it A. I should have called that X. That is a typo. Forgive me. And here is a proof of problem 20, and I will post this as well. There are other useful problems, and I guess I'm going to say how can we determine whether a relation is a function by examining the matrix? How can we understand if it is onto or not? And how can we understand if it is one-to-one? These are good questions for you to ponder and come up with answers, and when you do, we'll compare notes at the end of this. And here are the answers that I came up with, which I think are useful, and these are the answers that you should have come up with.